Hello Year 13s and welcome to our first little physics video. The idea is I'm trying to help you with simple harmonic motion, and simple harmonic motion usually involves circular motion. In school I would have a little rubber duck and a piece of string, but here we'll have to find an alternative, so let's have a look. Come with me. This work? No, but I think I have an idea. Okay, so as you can see, I found a rope and a chicken. So all I have to do is connect the chicken to the rope and I can demonstrate circular motion. Okay, so I've got the chicken firmly attached to the rope. Now we can commence with the circular motion. As you can see, the chicken is flying in a circle. I hope you appreciate the effort I'm putting into here. I'm now standing in front of my garage door up on a ladder together with my chicken. And I can now let my chicken do its circular motion and you can observe what the shadow does. Off we go. As you can see, the shadow of the chicken now is moving up and down in perfect simple harmonic motion. Whoop. Hey guys, so before I get any major complaints, I can totally ensure you that no chicken got harmed in the making of this video. Well, almost no chicken. Okay, so now it's time to talk through some of the theory about simple harmonics. And for this, we'll use a nice old whiteboard I could find in the back of my garage. So, starting off with a circle, that's our reference circle. So this is an imaginary point P that's going to rotate around that circle. By default, always in an anti-clockwise direction. And I'm going to attach to this a little vector from the center of my reference circle to this point. Now this is my rotating vector, otherwise known as a phasor. And this is going to show me now the amplitude or the displacement of the oscillation as the point is moving in circular motion. I've got another high-tech prop for you here. Surprise, surprise, another chicken. And this can show you, that's what the shadow of my chicken did on the garage door. It was moving up, down, back up again. So, at equilibrium, we had maximum velocity. At the very top, at the very bottom, chicken had to stop. So, if I look at my displacement phasor, here I've got zero vertical component to this vector, so I'm starting at 0. Quarter of a turn later, I've reached maximum amplitude. From there, I'll go down to 0, across to negative maximum amplitude, and back to 0, leaving behind a sine curve. Okay? So, I hope you remember that the angular velocity of an object that's rotating, omega, is defined as angle turn through theta over time. For a complete oscillation, the angle becomes 2 pi radians. And the time here, by the way, this time, the time period, the time becomes 1 period. Here we go. Okay? You might also remember that frequency equals 1 over period. So I can replace this 1 over period here and turn that into 2 pi f. Okay? Now, important to mention now is omega, which we before referred to as angular velocity. Now, with simple harmonics, this object isn't really moving in a circle, so we can't talk about angular velocity anymore. So omega, in terms of a simple harmonic, is now referred to as an angular frequency. Different word, almost the same thing. We're still turning, the object is still turning through 2 pi radians for an oscillation. Now we're talking frequency, therefore omega is referred to as an angular frequency. Alright, so this is our graph of displacement against time. What you'll see is that by the time my point P was up here, I've got maximum amplitude. Okay, and here I've got maximum negative amplitude. Graph's not quite nice, but it'll do. Okay, now in between, how can we figure out what the displacement is? Now the displacement at any one point is the vertical component of my displacement phasor. So if my phasor has moved on to, let's say, this position here, then the vertical component of it is here. Or in other words, this is the vertical velocity, the vertical displacement related to this phasor. I've turned through an angle theta, so I hope you recognize that this is the opposite to this angle. Therefore, displacement y equals amplitude A multiplied by the sine of theta. But theta here, I can rearrange this equation. Theta equals t goes across omega t. So y equals A times sine of omega t. Okay, so let's look at the velocity. So my point P here, that is traveling around my phasor, my reference circle, has a given velocity. At this moment in time, its instantaneous velocity is upwards at a tangent. And my object that's performing simple harmonic will have its maximum velocity at this equilibrium point. And you might remember from rotational motion that this velocity equals radius times omega angular velocity. Now, in our case, the radius is now the amplitude. That makes it V equals A omega, because this phasor here represents the amplitude. If we look at it over time, starting from here, I've got my maximum positive velocity. Quarter of a rotation later, I've gone down to 0 vertical velocity, because my velocity is now to the left, going on to maximum negative velocity, velocity vector pointing down, back to 0, back to maximum positive velocity. Now, at any other stage, let's say my amplitude phasor has turned through an angle of theta. By the way, this is now our A omega, maximum velocity, which is pointing this way at the moment. Its vertical component, here's my angle theta again, is now the adjacent to this triangle. Therefore, I've got cosine theta along here to get the adjacent. Therefore, the equation you'll find in your book, V equals A omega cosine omega t. Remember, theta is omega t. And for the last thing, we need to look at acceleration. So as my point P is moving around a circle, I think you all know the acceleration has to point inwards. Circular motion, this is your centripetal acceleration. The equation for centripetal acceleration equals v squared over r. Now, write that for our simple harmonic. The acceleration equals v squared. Velocity was a omega, makes a squared, omega squared, over the radius is the amplitude. So we're left with a equals a omega squared. As my phasor turns through an angle of theta, the acceleration now is still towards the center. So this is my a omega squared. So the vertical component of it is what I'm interested in. This is my acceleration. The angle theta is obviously here. Therefore, I'm looking at the opposite side of this triangle, the right angle triangle, which means I have to multiply by the sine of omega t. Now, one more thing here. The acceleration is always towards equilibrium. It's always in the opposite direction as the displacement. If the displacement is upwards, the acceleration is downwards. If the displacement is negative, the acceleration will be upwards, and therefore positive. This is why we have a minus sign in this equation. Now, to draw the graph again, we're starting at 0 here, because at this point in time we have an inward acceleration, therefore there's no acceleration. As my chicken moves through equilibrium, it's not accelerating. It reaches maximum negative acceleration up here. Therefore, it'll look like that, and back to 0, maximum positive, and back to 0. Over one time constant, it will be here. So, in the last few minutes, we've derived 3 equations here. One for displacement, one for velocity, and one for acceleration. Now, if you have a good look at your equation sheet, you will find another set of equations that look very similar. The difference between the two is that the equations I just derived with you all started from our amplitude phasor starting at equilibrium. The other equations, the bottom line here, are the ones you have to use when you start at maximum amplitude. Whether it's positive or negative doesn't matter. If you're starting your time, you're releasing an object from maximum amplitude and you're observing it, these are the equations to use. Top equations, when the time starts equilibrium. Bottom equations, when the time starts at maximum displacement. I think it's a really good idea for you guys to derive these equations from the reference circle, just like I've done for the top 3 equations. Give it a go. Good luck. And as a final comment, no chicken got wasted in the making of this video either. So, eat well and stay safe.